Hello students, today we'll be going over the crossed aldol condensation. So this begins with our synthesis of our actual aldol, followed by the condensation of the aldol. Now, to start out with, I'd like to explain a little bit about alpha hydrogen and alpha carbons. So carbons that are right next to the carbonyl carbon, connected to the carbonyl carbon, these are referred to as alpha carbon, and the hydrogen attached to them are referred to as alpha hydrogen. Now these alpha hydrogen, they are a bit more acidic than a normal hydrogen would be on an alkane. Through induction, through this carbonyl group here, the electron density around the proton is pulled away, allowing it to be slightly electropositive. So this allows it to be more acidic. So if a base comes along, such as this hydroxide ion here, it is more easily abstracted. And that is how our aldol synthesis begins. It begins with the introduction of a base. So we'll be using sodium hydroxide in our reaction. So we'll have a hydroxide ion pulling off our alpha hydrogen, our alpha proton, to create water. And the bond, or the electrons making this bond, will be transferred to this the alpha carbon. So along with that, we have our enolate formation. So with the electrons are on this carbon and this double bond is unmoved, but this also has a resonance structure with bouncing back and forth between this double bond in this alkoxide and this normal aldehyde group with an electrophilic carbon, or nucleophilic carbon. Now this carbon, it's unusual to be working with a nucleophilic carbon. Normally we're used to electrophilic carbon, like here on the carbonyl carbons, but this is an uncommon instance in which we will have a nucleophilic carbon. So this is another example of carbon-carbon bond formation, which is very, very useful in organic synthesis. So with our enolate, with our our pair of electrons here on this carbon, this will attack another aldehyde, as we have here. So this can all happen to the same chemical, so one aldehyde attacking another. Oh dear. Okay, well, I'll just keep going. So with this, the nucleophilic carbon will attack the electrophilic carbonyl carbon, pushing off these electrons. Are you serious? Okay, I'm glad this is just a practice round. So let's see, pushing off these electrons onto the oxygen. And so with that, we have our our bond formation here. So we have our carbonyl carbon and our alkoxide. So with that, the water molecule floating around in solution, likely added with the sodium hydroxide to form our hydroxide ion. The alkoxide will pull a proton off of the water molecule, and this will form our final aldol. So this would be a form of a beta hydroxyaldehyde. So here's the aldehyde group, and if we have alpha carbons, we also have beta carbons. So we have a hydroxyl group attached to the beta carbon, forming our beta hydroxyaldehyde. So aldol, as you can see now, is aldehyde and alcohol. So together they just make the word aldol. So this reaction is also reversible. So with a hydroxide ion being able to abstract the slightly acidic alcohol proton from our hydroxyl group, with that forming our alkoxide and one of the lone pairs reforming the double bond and breaking off the bond between the beta carbon and the alpha carbon, and reforming our enolate and our aldehyde. As well, we have our aldol condensation. Now that we've synthesized the aldol, we're able to perform the aldol condensation. So it begins with an elimination reaction with the hydroxide ion pulling off a proton from this alpha carbon. So this alpha hydrogen is being abstracted, and normally this this part of the reaction is heated in order to increase the ability for this reaction to take place. So with that, the electrons that were forming the bond between the carbon and the hydrogen, they will be placed onto the this carbon. So here we have another nucleophilic carbon, but these electrons here then can form a bond here, pushing off these double bonds onto the oxygen, creating an alkoxide. So with that, the alkoxide doesn't really want to stay an alkoxide, so it can reform this double bond, pushing this double bond over here and breaking off our hydroxyl group. Now normally hydroxyl groups aren't very good leaving groups, but we're doing this in very basic conditions. So in this case, the hydroxide group can act as a decent leaving group. And with that, we have our final formation of our alpha beta unsaturated aldehyde. So this bond here is a double bond. It is not saturated with hydrogen, so it is an unsaturated bond. So with our particular reaction, we will be forming dibenzyl acetone. So here we'll begin with our aldehyde, our ketone, acetone. So this time, instead of it being an aldol attacking an aldol, it'll be a ketone. An aldehyde attacking an aldehyde. It'll be a ketone attacking an aldehyde. So here another hydrogen abstraction, or a proton extraction from our base. It will be using sodium hydroxide, forming our enolate, which our nucleophilic carbon will be attacking the electrophilic carbonyl carbon, pushing off this double bond onto the oxygen, forming an alkoxide. And with that, we have another proton extraction from the water in the water in solution, which would have been added with the sodium hydroxide. And with that, we will be forming an aldol, another aldol, but only temporarily. And with that, we have one more proton abstraction, but here from the alpha carbon. So we have another alpha hydrogen, still acidic. And with that abstraction, we have our double bond reforming here, pushing off our hydroxide group once again, and pushing off our hydroxide group, and we have a double bond here with our phenyl group here on the end. So this all happens again on this carbon instead, forming our final dibenzyl acetone. But the thing is, our acetone itself doesn't have to react with the aldehyde. It can react with another acetone. And when that happens, just a quick walkthrough of mechanisms. With our proton abstraction, our nucleophilic carbon attacking our carbonyl carbon of an acetone instead of an aldehyde, and this will form our alkoxide, and then our final, a abstraction of a proton, a removal of the hydrogen from the alpha carbon, and in the end we'll have a methyl oxide. So this will be an impurity if we're seeking to make our dibenzyl acetone. So something else that we'll have with our when we are making different aldol synthesis, we'll have a double bond species, or double bonded molecules. So when that happens, we're able to have different stereoisomers. So this means cis and trans, E and Z. So in this case, normally the trans molecule will be the more stable product and usually the major product. So in this case, we have dibenzyl acetone. We'll have two separate parts of the molecule able to be cis or trans. So we'll just have different stereoisomers. We'll have for dibenzyl acetone, we'll have 3 in all. Cis-cis being a very minor product, Cis-trans being more likely but still considered a minor product. And then our major product will be trans-trans dibenzylacetone. So, thank you for listening, and I hope you enjoy the lab.